Action.
Okay, so here's the difference between horizontal centripetal motion when you have this action going, like you did in the lab, which you all need to hand in today.
I handed
Danny's
it
the
in.
only one that's handed his in.
Oh, okay. Mine's in the basket as of now.
Good. So, in this situation, you have two forces. You have the centripetal motion acting inward, okay? Any centripetal force, whether it's a strain, gravity, friction, doesn't make any difference. Do not overthink it. If I ask you, what's the direction of any centripetal force? It's inward at a right angle to the velocity vector. There's nothing pushing you out. There's no centrifugal force, which is a bogus force. It doesn't exist. It's what you feel, but when I swing this thing around, whether it's horizontal motion or if it's vertical motion like this, there is no magic force emanating from my hand to put that thing out, okay? There's no centrifugal force pushing the Earth outward in its orbit around the sun. It doesn't exist. Now, here's the problem though. If you're inside the car and you take a turn and you feel like you're being pushed against the car door, within the frame of reference of the car, you go, oh yeah, right, okay, yeah, I feel like I'm being pushed, okay? Or pushed, if one of my brother-in-laws cannot say the word push, is poosh. I was pushed up against the car. No. There's no magical force that exists to push you out anywhere. Does your body have mass? Yes. Does your body resist an acceleration? Yes. Do you exert an equal and opposite force against the car door? Absolutely. But centrifugal, remember, means outward seeking. There is no outward force pushing you against that car door. Okay? Doesn't exist. So, when you deal with vertical motion, though, now you have to worry about gravity. So you have two extremes. One, you have the gravitational force acting down. So this is what you want to look at. So at the bottom, this is why you cannot be in a state of weightlessness at the bottom. Because remember, this total force, that's what you are going to experience. So right now, you all are sitting within the context of this room, and you're not accelerating. Okay, technically you are because the rock is spinning. So right now, if you look at this equation, your total force equals force centripetal plus Fg. Right now, you have no centripetal acceleration within this rim. So what you're experiencing is just mg. You are pulling 1g. Okay? You sit here, you're pulling 1g. That's it. You're pulling 1g. Now, imagine that I could take this room and put it on a pendulum and start to swing it back and forth and back and forth. When you're at the bottom, you're going to feel heavy because not only do you have to overcome the gravitational force, plus you have to make your body move in a circle. If you take it to an extreme and you make it go all the way around up to the top, okay? So if you're up at the top, then you subtract these values. Because when you're at the top, you need a certain amount of centripetal force to make that rubber stopper go around. You need X amount of centripetal force, no matter what, 10 newtons, whatever that is. When you're at the top, though, gravity is in effect helping you out. So it's just like, hey, Cohen owes me 10 bucks. Okay? Oh. He handed in a bunch of late work because like, Cohen, you owe me a 10 spot. Will goes, Cohen, I'll take pity on your soul. Just go with the story, okay? So Will, out of the kindness of his heart, pays for the $10. He goes, Mr. Brookcamp here, let me help Cohen out. Here's $4. Okay? So Cohen still owes me 6. I need my 10 bucks. Okay? You're like gravity. You're paying part of it. So the tension in the string is going to make up that difference, which is Cohen, which is still going to owe me the $6. I need 10. Now, if you're on an inside loop and if you're not going fast enough, you don't complete the loop. So on that first question, where it says, is this thing going fast enough when that 2 kilogram mass is being swung around? There's a whole bunch of different ways you can calculate that answer. You can calculate the minimum velocity that you need, V equals the square root of girth. You could find the total force at the top. If that's a positive number, you complete it. If your centripetal acceleration is bigger than 9.8 meters per second squared, you complete the loop, okay? Just don't tell me, oh, yes or no. You have to give a mathematical justification for that. Now, when you get to number 5, let's talk about that one, Sean. So on number 5, you want to feel 1/4 of your weight. So you have to be at the top to pull this off, and here's the reason why. Because the total force equals force centripetal minus Fg. Okay, that's what you got. So if you're at the bottom, you're always going to experience at least 1G. Okay, you cannot weigh less than what you weigh now at the bottom. If anything, you're going to weigh more. So this can only happen at the top. So you've got 1/4 Fg equaling Fc minus Fg. So what I would recommend is that you go, oh, that's mg, that's mv squared over r minus mg, your masses cancel out, you move that over, you do a little algebraic hocus pocus, and you get the 5 force of Gur, gives you that velocity. So all of your answers on 5, the mathematical, should be somewhere between 15 and 21 meters per second.
Which ones? Between what?
On 15, somewhere between 15 and 21
Wait.
meters per second.
On
Not what you had before.
On 5.
5? Okay, 5.
Five.
Between
Yeah, that was
15
the
and
train.
21.
You didn't take into effect
I don't
that.
know how.
Your answer on that yellow sheet, your answer to number 6 would make a not so good GPA, not horrible, but not bad.
I just forgot to take the root.
Your answer to number 7 should be something times 10 to the 4th.
Yay. There's
Yes.
And this tends to happen like on the questions out of the book, like on 25 and 26. Keep in mind, those are multiple choice questions. Do not give me the numeric answer. These are multiple choice answers. Yes, you have to come up with a numeric value, but do not just write down the numeric value. There's a letter that corresponds with that. On the problems out of the book, your answer to number 16 should be less than 1.
That would make sense considering.
It's a coefficient of friction.
Yeah. Wait, I was being not smart. Can you... Sorry, I've got multiple assignments sitting on my desk right now. 23... 11? I wasn't sure, like, I understand...
Which 11?
So
It's literally just the car going over the hill, but like, I see the free body diagrams, my brain is not like
20.
Okay.
computing. Like, I understand, right, the car goes over, once you continue in a straight line, but
Calm down.
Okay. So on question 11, here's the story. So which of the following about is correct? So here's what you want to look at. So as you come up over the top of the hill, let's just say you were sitting on top of the hill. Okay?
okay,
What would you know about the forces?
they'd be in equilibrium, it'd be force normal would equal force gravity.
Yeah, you'd have two forces like this, right?
Right.
True. Okay. Now, you're coming up over the top of the hill. What does the car want to do?
Fly away.
Wants to fly away. So imagine that you had a scale
Yeah.
that was keeping track of the weight of the car. When it came over the top of the hill, what would happen to the reading on the scale?
It would go lighter.
Oh, that's what
Okay.
I meant.
So it should be A.
I don't know. I'm
More
just
force,
telling you-
more force up, less force down.
I'm not telling you anything. All I'm just telling you is Now, make sure on question number 11 where it says explain, you want to give an explanation. All right, so let's talk about
Oh, yeah.
problem 52, because that's a cool historical question. Because it's somewhat relative to what we're going to talk about today. So, let me you need to really understand 52, you need to understand the historical perspective, okay? So, if you look at like the history of science, there was the great quantum age, which is kind of like the late 1910s into the 1920s. This is all done in Europe. You had Heisenberg, Bohr, Schrodinger, Einstein, Max Planck. You had all these physicists that were working on this, and it was just basically one great discovery after another, after another, after another. But it all started with Ernest Rutherford. So remember, Rutherford said, okay, here's the sheet of gold foil. He had the radioactive source. He shot the alpha particles, which you could not see because they were a helium nucleus, but they would interact with the phosphorescent screen, and you would see a flash of light wherever that alpha particle struck the phosphorescent screen. So this thing would come in here. He had this gold foil that you could not see through, but it's gold foil, okay? Because you can take gold foil and literally work it down to like 1 or 2 atoms of gold thick, because gold has such a unique property to be malleable. And so he shot these particles at it, and the vast majority of these particles went straight through. Okay, there was no deflection at all. Literally 1 in a million times, it would hit and it would bounce back. And we'll talk about this when we get into energy. So basically what happened is that particle left with a certain amount of kinetic energy. That gets converted into EUI, which is electrical potential energy. So on the one that would bounce back, this alpha particle, here's this big massive gold nucleus. It would come into here, stop, and bounce back. But here's why this happened 1 in a million times. Imagine that I've got Hank at that end of the room, and I'm going to throw a marble at Hank, okay? Literally, there's Hank in the back of the room, okay? Hank's back there. I am this far away and I'm throwing marbles at Hank. Vast majority of the time, what's going to happen?
You miss Hank.
I'm going to miss Hank, okay? Every once in a while, I might hit Hank, but it's going to glance off, okay? Vast majority of the time, the marble is going to go straight through it. Every once in a great while, I'm going to get lucky. And I'm going to hit Hank dead middle. That's the only way this is going to happen. Is if I hit the exact center of Hank. And if I hit the exact center of Hank, that marble is going to come back. But that's not going to happen very often. So, Rutherford came up with 2 primary conclusions from this. The atom is mostly empty space. All of the mass is located in the nucleus. And that nucleus is positively charged. That created a problem. How do you keep all the positive charge inside that nucleus? That led to the discovery of the strong nuclear force. So at this point, now, you have to keep in mind, all of the people doing this research were physicists, okay? They aren't chemists, they weren't biologists. This is strictly their own physics department, basically because they didn't have anything else to do at the time. They thought they'd work themselves out of the job. So this is like, oh, we have research opportunities. Thank you very much. Okay? So, because they were physicists, they said, ooh, this is cool. In their mind, they had all studied gravitational motion, which is what we're going to start talking about today. This is why this is a nice segue from this into gravity. So they said, this is cool. So, in their mind, they were just going to take the solar system where you had the sun, and then you had Mercury and Venus, and you have Earth, okay? And these existed in well-defined orbits. Ah, right. They're accelerating because they're going around the sun, and they had all studied centripetal motion. And they said, this is cool. So in their mind, they took the model of the universe, and they shrunk it down. And they said, instead of the sun, you have the nucleus. Instead of planets, you have electrons. Cool. It fit their mindset. There were some problems with it, because it would be like me swinging this rubber stopper around, and the rubber stopper could exist at this distance, or it could exist at some other distance, but that's it. So, hey, that's it. Like the rubber stopper could not exist at any other point. Like there's very defined orbits. That's a little bit of a problem. The other problem is that because the electron is going around in a circle, it's accelerating. And we'll get into electromagnetic field later in the spring. But when electrons orbit and they accelerate, they should emit radiation because they're accelerating. And if they're accelerating and they're emitting radiation, they should lose energy. And if they lose energy, what should happen is this, okay? The electrons should all collapse into the nucleus. Small problem. Because they don't. I've had this table since the fall of 1994. Okay, this is my 30th year of teaching behind this table. It's still a table. The electrons haven't collapsed. The nuclei are still stable. It's still 99% empty space. It looks solid, but it's actually empty space. So,
They get your velocity.
in their mind, they said, hey, we're just going to take the equations for centripetal force and shrink that down to the atomic size. Nucleus, electron, frequency, hey, all this stuff. So if you look on 52, you got a hydrogen atom, electron, 9.1 times 10 to the negative 31st. That's a number that we're going to use a lot. So you got the mass of the electron, which in and of itself was an extremely difficult challenge. Like, how do you find the mass of a single electron? It isn't like you could take a pair of electron tweezers and go into a jar of electrons and go, oh, I'll just pull out an electron or I'll put it on the scale and get a reading of 9.1 times 10 to the negative 31st. So, and this is going to play out large today as well. But it's the same thing when you find the mass of a planet, Saturn, Jupiter, whatever. It isn't like we send a space probe to Mars or Jupiter or any planet and go, hey, let's find the mass. Oh, we'll take the planet, we'll stop it in its place, we'll put it on a scale, we'll give the reading, and then we'll put it back into orbit. Okay, this isn't like a catch and release thing with fish like you do with planets. Okay?
Dang
You
it.
can't do that.
I want to catch a plane.
So the same thing is true of electrons. You can't just take an electron, put it on a balance and go, oh, that's the reading, here it is. No. And later on when we get into, like I said, electromagnetic field, you figure out how you use electric fields and magnetic fields, and you make it travel in a circle, and that's how you figure out the mass of it. So here's the story. So you got the mass, orbits a proton at a distance of 5.3, the proton's pulling the electron, force of 8.2 times 10 to the negative 8. How many revolutions per second does the electron make? So there's a couple of ways you could approach this. One is that you could go centripetal force equaling mv squared over r. Okay? You know the amount of centripetal force, which is what's creating, which is that electrostatic force. You know the mass of the electron, you know the radius. Okay? You find the velocity, you go velocity equals 2 pi r over t. You solve for t and then go, oh, period is 1 over frequency, so frequency equals 1 over period. Okay? That's an option. So if you like kind of piecemeal problems together, you can do that. But let's think about this though. Is your answer to 52 going to be a really, really big number or a really, really small number?
Big.
It's going to be a really big number because you're talking about the frequency of revolutions of an electron as it goes around the nucleus. Okay? So if you get a really, really, really small number, that's bad, okay?
Your electrons are moving very slow.
So this is an option, okay? Now, if you go through, you could also go centripetal force equals mass times 4 pi squared r over t squared. Because if you take 2 pi r over t and put that into this velocity, you can get to this equation. You could do this, and you could find the period, and you could take the inverse of that. Or you could go, oh, well, that's mass times 4 pi squared r, and then instead of period, you put 1 over frequency squared, and then the frequency squared flips up, and then you can just do it all in one equation. Okay? Regardless, your answer to number 52 is a really, 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 really big number.
Can you tell us what the coefficient of 10 is?
Your coefficient should be probably a little bit less than your age right now.
Oh, less? Less, okay.
The coefficient on 52 should be probably less than your age right now.
Oh, that's really bad.
Screwed up. How much less is yours?
What do you have got, Sean?
Also,
6.56.
I saw a problem with yours.
You got the-
it's your-
Wait, you got 6.56?
1.52?
Right?
No.
Okay, you asked for the exponent.
Yeah.
Oh, yeah, excellent. Okay, yeah. Oh, okay, yeah, the expo. Yeah, okay. That's good.
Wait.
You read it for me?
Okay, my
That's what
ex
you asked
Yeah,
for.
that's what I asked for.
Berg, my exponent's 22.
Mine
Is what?
22.
Okay, mine's
Oh,
not-
God, you're so far
This
off.
is pretty easily verifiable.
It's 15.
Like, you can check your answer. This is known information.
Hey, what coefficient of 10
Oh,
did you
yeah.
get?
Coefficient
23.
10 or like exponent of 10.
Exponent of 10.
It's definitely known a
15?
little bit
So
less.
Oh,
like
that's
15
17.
maybe would be less than your age.
Let's see your first.
Okay,
What's your T?
T?
I'm just gonna.
What's T?
Your answer to 62, because 62 is kind of a cool question because it combines centripetal motion and gravity. So your answer to 62 should be between 10 and 15.
No, I'm starting to feel like my entire paper's wrong now. After
No,
having
because
it
usually, what's this?
I just like assume that every time.
Using
That's
this one,
comforting.
you wanna use this one first.
Nothing is real.
Okay, I don't
I'm
do
gonna have to
I
do
can't do
that.
number 20.
Okay.
I still can't do number 20.
Is that
I don't
fine?
know why. I did it 3 different times and I still like you're getting the same exact answer.
Oh, that one.
For which one? 20?
Yeah, for 20, I don't know.
All you have to
This
do
is
is just
where I
use
found it
this,
from,
mass 4 pi squared
Into
r times frequency
our,
squared.
meters per second
And
to.
it's getting like 202 for the acceleration.
Yes.
Don't lie. Why? Why?
Yeah, and then I just
Why are you finding the acceleration
I mean-
separately?
I mean, okay,
what?
but my total force is like 2.424 times 10 to the 6 or something.
No, it is 10 to the 6, but that's not it.
It's exactly half of
I
that.
don't remember seeing.
Okay, let's talk about 20. Here's the trick on 20. This is probably why. So, you got a 12,000 kilogram wind turbine blade like this, right? So if you look at centripetal force equals mass 4 pi squared r times frequency squared. One option is that you do this for every piece of mass that's on there, okay? Because it isn't like it's a single blade. It isn't like it's a rubber stopper going around, okay? So, and we're going to use this technique when we do gravity problems. Physicists are known as treating it as a point mass. You take a cow, you can treat it as a point mass. A sheep, the earth, will. Okay? Anything can be treated as a point mass. So if you treat it as a point mass, and that's the whole key to this, you treat it as a point mass at the midpoint of the blade. So what's the entire length of the blade? 38 meters. So where's the midpoint?
I think we put 0.2, so I reckon it's 882.
What's the radius of the midpoint of the blade?
The midpoint?
19?
Oh, so you do 19 instead?
That's what it says. The model of the blade is a point mass at the midpoint of the blade.
Yeah, come on.
Oh my
guys.
gosh,
Just
I'm
ignore
so
that.
dumb.
Yeah, come on, guys.
Oh.
It says
I can
the
read.
midpoint of the blade.
I just need to erase that, make that
How
that.
you got like
This is exactly half of
you
that.
read the
We don't talk about that.
the force.
That becomes 101.
Crazy.
Yeah, I think it's
I still got the wrong answer.
1.37.
I got it.
That becomes
I don't know, I
101.
just did it all in one step.
That
I didn't
becomes-
find the acceleration stuff.
Yeah, I am not doing it right now.
1.21.
I have a total answer. I found the answer 1.37. times like-
Whoa.
What is it?
I know.
No,
from
1.21.
me, I'm
I'm gonna hope for
Oh,
at least,
okay.
at least
Can I just
a
not do
90.
my
When did you
calculator right? What am I doing?
Bro, you just half it.
Times.
Think about it. If you did the full radius.
Okay, really, it should be 2.424
to
divided by
find
two.
our
1.21.
to
Yeah, it should be
because I
that.
could not find it anywhere.
Hey, that's not right. It should be a little less than right.
Yeah.
At least I did the assignment this time, Berg. Or at least most of it. 24
No, our-
and 62, I.
You're just
No,
taking
he said
those.
the coordinate.
No.
Okay,
I'll have them done
stop
by the
on
end of
camera.
class.
10.